Good afternoon, everyone. Welcome to the 7th annual meeting of TCS for All workshop. I'm Sumega, one of the organizers for TCS for All. Other organizers are Berna, Deberti, Elena, and Virginia. As part of the workshop, we have an annual inspiration talk where we get to hear from the works and experiences of our leading experts in our field. This year, Professor Luca Trevisan had very kindly accepted our invitation to be the annual inspirational speaker. We are deeply saddened to get the news of his passing away last week. His absence is deeply felt by all of us who has admired his work and contributions to the field. Before we hear his talk that he prepared for us in his last few weeks, Professor Barna Saha will say a bit about TCS for All, and then I'll go towards the introduction.
Thank you, Sumega. Yeah, so just a little bit of history for TCS for All. So we started in 2018 when STOC started its Theory Fest. And at that time, our goal was to support students who otherwise couldn't have attended STOC and Fox. We realized like how important it is for their career. So since 2018, we are providing travel scholarships. By the way, so in 2018, we used to call it TCS for Women. So we are providing travel scholarships to women students from 2018 onward. In 2019, and we also organized panels, just like lunch panel over lunch session. In 2019, we added the TCS for All Inspiration Talk and TCS for All Rising Star series. And that we included everyone. And in that spirit to make it more inclusive. So from last year, so TCS Women, which was TCS Women in 2018, became TCS for All. So as Sumega mentioned, like as part of the inspiration series, we always have an inspiration speaker who is the thought leader, head turner of our field. And not only that, who is deeply committed to developing the TCS community. So this year, when we are deciding, so we decided to invite Luca Trevisan. So Elena Grigorescu and I reached out to Luca in April, inviting him to be our speaker. So at that time, we learned about his cancer. And he told us that it might not be possible for him to join in person, but he still agreed to give the talk over Zoom. And he was very hopeful that the treatment might work and he can be online on Zoom. And we were also very hopeful that the treatment would work. So last week on June 16th, we learned that the treatment failed and Luca has only few weeks left in his life. So we reached out to him. We said, we are with you. You don't have to worry about this talk at all. And he responded back on 18th, just a day before he passed away. He said that he has prepared slides and two other folks, in this case, Salil, Vadhan and Pravesh Kothari, will present the talk that he has prepared. I cannot even imagine what kind of physical exhaustions he was going through during those times. And it's like unbelievable that during those times, he spent the time to prepare this talk. So to me, it's like the epitome of inspiration. If this is not inspiration, I don't know what is inspiration. And we are deeply honored to have Luca Trevisan's last talk being given through TCS for All. So by the way, so after the inspiration talk, we do have Rising Star Speakers talks in the afternoon, and we have an Ask Me Anything session after from 1:30 to 2 p.m. So with that, Sumega will now give an introduction to Luca. Sumega.
Yeah, thank you, Berna. So yeah, Luca was one of the great minds of our field, and he had a prolific scientific career. He received his PhD from La Sapienza University in Rome. He held faculty positions at Columbia University, UC Berkeley, and Stanford University before moving back to his home country, Italy, to join Bocconi University in 2019. His pioneering contributions in pseudo-randomness, complexity, cryptography, and algorithms has had a profound impact in theoretical computer science. Throughout his career, he has had He received numerous accolades for his outstanding research. To name a few, Luca was a fellow of the ACM and the first computer science member of Italy's National Academy of Science. He received the 2000 Oberwolf Prize and the 2000 Sloan Fellowship. He was an invited speaker at the 2006 International Congress of Mathematicians, and in 2019, he received the ERC Advanced Grant. This is just to name a few of his accolades over the years. Luca's contributions go well beyond his research work. Luca had a long-running blog called In Theory, which he started in the early 2000s. It's truly an inspiration for all of us. The blog is really a treasure full of expositions about current technical advances, beautiful and fun stories, and lecture notes, which are a learning source for all of us young researchers. In 2012, he organized a very thoughtful guest post series for the Turing Centennial Year, where many of the LGBTQ plus members of our community shared their experiences in academia. He has really been he is a really inspirational figure, and the number of people that have joined today to listen to this talk, both in person and Zoom, are a testament to his life as an incredible researcher and a wonderful human being. And as Barna mentioned, despite the health challenges, he prepared slides for the inspirational talk that we will hear today. And this talk would be given by his friends and collaborators, Professor Pravesh Kothari and Professor Salil Vadhan. So before I invite them to give the talk, let's take a moment of silence to remember Luca and pay our respects to Professor Luca Trevisan. Thank you. I'll invite Professor Pravesh Kothari to start off Luca's lecture. Yeah, so it will first come here. Oh yeah, that's right.
Yeah.
Yeah.
Is that good? Thank you all for coming. So this is a talk prepared by Luca Trevisan in his final weeks. Luca has been and will continue to be an inspiration, especially for us theoretical computer scientists. Not just because he was a researcher with profound contributions to multiple areas of theoretical computer science, not just because He was a gifted expositor, especially through his blog, and was a reason for a number of people trying to get into new areas, including myself. But also because he was a reliable mentor, always ready to help navigate research and life as a researcher to anyone who approached him. A lot can be said, but I will try to adhere to the original goals of TCS for All and Luca in this talk. So the first part of this talk, which I will give on behalf of Luca, is about spectral graph theory. Yes, so the first part of this talk is about spectral graph theory, which in Luca's own words was one of his favorite areas of theoretical computer science. Specifically, it's going to be about two threads of research, each of which address fundamental questions about graphs. But perhaps surprisingly, the ideas that lead up to these results also have consequences. In fact, they lead to resolutions of old and important problems in mathematics. In the course of discussing these two results, we will see, among others, two theorems of Luca, which, in my opinion, are landmark results in the development of spectral graph theory. And if this is an area that you haven't encountered before, or maybe haven't taken interest in, hopefully Luca's talk will inspire you to take a closer look at it. Okay, so let's begin. So at the heart of it, spectral graph theory is the idea of associating some natural matrices with a graph so that you can study combinatorial properties of the graph by looking at eigenvalues and eigenvectors of these matrices. What this allows in particular is to use linear algebraic tools to address combinatorial questions about graphs and to even design algorithms for solving combinatorial problems on graphs. Now, this is perhaps the more well-known view of the theory, but the reverse connection, even if little less known, turns out to be equally powerful. In particular, we can go back and use graph theoretic intuitions to attack questions in pure mathematics, specifically linear algebra and operator theory. And this connection indeed has been fruitful in resolving some main questions in those areas of pure mathematics. And this is one of the key points that Luca wanted to make in this talk. So for the two vignettes that Luca will present in his slides, he will first discuss the results themselves, and then how they naturally connect to interesting questions in mathematics and in fact lead to resolutions of them. Good. So one reason that Luca wanted to talk about spectral graph theory in his talk is because recently there's been quite a few developments that try to build analogous theories, analogous spectral theories for hypergraph and tensor problems instead of graphs and matrices. And this even allows us to approach questions about nonlinear operators, which can be represented as low-degree polynomials. Perhaps a little bit more speculatively, Luca wondered if, we could use ideas or foundations such as these to study alternations of linear and nonlinear layers that occur, for example, in neural networks, and perhaps, more hopefully, come up with models which are different from the presently used models in AI that nevertheless are more easily rigorously analyzable. So that was the motivation. Let's see, the first vignette in what Luca wanted to present. So this first vignette is about the use of eigenvalues in order to solve clustering problems in graphs. What that means is that I want to take a graph and partition its vertex set into, let's say, two groups, so that the connections between vertices across groups are tenuous in the sense that they are sparse or not so well connected. This is called clustering because you are separating the vertices of the graphs into two groups, such that the groups themselves are well connected within themselves, but not as well connected between them. In order to begin, let's recall spectral graph theory 101, so to say, which means that we will study some natural matrices that perhaps all of you have looked at and associate them to graphs, and then talk about how their eigenvalues relate to interesting combinatorial properties of graphs. So the most well-studied matrix associated with the graph is, of course, the adjacency matrix. The adjacency matrix in particular happens to be Hermitian if the graph is undirected. In particular, it's a symmetric matrix, which makes its eigenvalues real. Actually, it not only makes the eigenvalues real, it allows a definition of eigenvalues as solutions to some natural optimization problems associated with the adjacency matrix. This view of eigenvalues as solutions to an optimization problem, Luca will discuss this optimization problem very soon. This is the key for why this theory works. In particular, not much of what Luca will try to present today would apply to directed graphs because the symmetry property of the adjacency matrix is lost. Now, if you wanted to use eigenvalues to study combinatorial properties of regular graphs, then the plain old adjacency matrix suffices, in the sense that you can do almost everything you would like to do with just the adjacency matrix or some simple normalization of it. But if the graph happens to be irregular, it is much cleaner to work with the so-called normalized Laplacian matrix, which Luca will now define for you. Given a graph G, you can associate a diagonal matrix with the graph, which simply in the v, vth entry notes the degree of the vertex v. Given the adjacency matrix, you can take the shift of the adjacency matrix, where you simply take the matrix D minus A, meaning the diagonal matrix of degrees minus the adjacency matrix. This is called the Laplacian matrix. Okay, it's very simple. It's simply a shift. The normalized Laplacian is obtained by rescaling the rows and columns of this matrix. Notationally, what this means is that you take the matrix, which is also diagonal, but this time the entries happen to be inverse square roots of the degrees of the vertices. That's what d to the minus 1/2 means, and multiply it on both sides. So that's that's basically how you get normalized Laplacian. Now, this notation might be complicated, but for regular graphs, it's very easy to understand what it looks like. Namely, the regular graph, for deregular graphs, this normalization operation simply corresponds to taking identity minus 1 over d times the adjacency matrix. You might have seen 1 over d times the adjacency matrix being called the random walk matrix of the graph or the normalized adjacency matrix. So it's, this normalized Laplacian is simply, a shift of the normalized adjacency matrix by identity. The point of Luca is telling you about normalized Laplacian is that for most purposes, whatever you can prove with the normalized Laplacian for deregular graphs, it turns out, perhaps with just a little bit of notational effort, extends to irregular graphs by just working with the normalized Laplacian in more generality. So for the purpose of this talk, I would invite you to simply consider the case of deregular graphs with the backdrop that everything that Luca is trying to present would generalize appropriately to irregular graphs by working with normalized Laplacians. Okay, now the Laplacian and the normalized Laplacian matrix. The Laplacian and the normalized Laplacian matrix of a graph are positive semi-definite. What that means is that all the eigenvalues of these matrices are non-negative. And what we're going to do is order them in ascending order. This is what gives me the notation lambda 1, lambda 2, lambda n, lambda 1 being the smallest eigenvalue of the normalized Laplacian and lambda n being the largest. Lambda 1 is very easily seen to be 0. In particular, for regular graphs, just imagine the vector, all of whose entries are +1s. Then the quadratic form of this vector on the Laplacian or the normalized Laplacian is 0. In particular, that tells you that the smallest eigenvalue must be 0. Now, a cool fact is that the multiplicity of the zero eigenvalues, meaning the number of eigenvalues that all happen to be zero, is exactly equal to the number of connected components of the graph G. So the first link between eigenvalues of the normalized Laplacian and the combinatorial idea of connectivity of the graph. Coming back to the bottom eigenvalue, it turns out it's, almost always at most 2. And in fact, it's equal to 2 if and only if there is a connected component of the graph that happens to be bipartite. So what we've learned in just this sequence of basic connections is that the top eigenvalues, in fact, the zero eigenvalues, somehow capture the connectivity structure of the graph, and the bottom eigenvalue relates to its two-colorability or bipartiteness. Even though if you've not seen this before, these connections might sound remarkable, the proofs of them are essentially one-liners. So even though they are very simple to prove, these properties are extremely powerful. Great. So here is one consequence of what Luca showed you on the previous slide. Since the multiplicity of the zero eigenvalues controls the number of connected components, one easy corollary is that lambda 2 is 0 if and only if the graph is disconnected. Once you look at this statement, it's very natural to ask, what might it mean for lambda 2 to be small but non-zero? And this leads to an approximate version of the theorem written in front of you. The approximate version goes by the name of Cheeger's inequality, which effectively says that lambda 2 of the normalized Laplacian matrix is small if and only if there is a subset of vertices in the graph such that most of the edges incident on the vertices in this subset are within the subset itself, meaning very few edges which are incident on these subset of vertices go out of this set. Formally, the fraction of edges incident on a set of vertices that go out of it is called its conductance. So, Cheeger's inequality says that lambda 2 is small if and only if a set of vertices has small conductance. Quantitatively, you have what is written on the slide at the bottom. Phi is simply the minimum over all possible sets of size n over 2. Think of it as like looking at the smaller size of the cut, if you will, of the phi of s, where phi of s simply means the fraction of edges incident on s that go out of s, like I discussed. So phi is this, worst possible expansion or conductance of a cut. And the inequality says that if lambda 2 is, so the first direction, the so-called easy direction of the inequality says that phi is at least lambda 2 up to a factor half, which means that if lambda 2 is large, then every cut has high conductance. The other side, which is often called the hard direction of Cheeger's inequality, says that the reverse is also true. If lambda 2 is small, then there must be a cut with small conductance. And quantitatively, phi is at most square root of 2 times lambda 2. This inequality goes by the name of Cheeger after Jeff Cheeger, but he actually did not quite prove this. Luca reminds us that Jeff Cheeger really proved a version of this inequality on Riemannian manifolds. The inequality, as stated on this slide, actually was proven in the context of studying random walks on graphs. But the proof, in some sense, really looks similar to the ideas that Cheeger had in the context of Riemannian manifolds. Finally, I should have pointed out earlier, all the callouts are my corruptions to Luca's slides. So if you have problem with the callouts, you should blame me. The natural question you can ask, sorry about this callout. The natural question you can ask is when lambda, so you have this inequality which says that there must be a cut of small conductance. You can ask, can you efficiently find such a cut when lambda 2 is small? And it turns out there is a very simple algorithm called Fiedler's algorithm, which in some sense even predates the inequality itself. It was actually a practical algorithm that people were using to cluster the graph. Uses the second eigenvector, meaning the eigenvector corresponding to lambda 2, to do some natural rounding and get a sparse or a badly corrected cut. The proof of Cheeger's inequality in some sense can be thought of as analysis of something very related to this Fiedler's algorithm. To finish with, I only want to point out that there is an authoritative source of this for people who have taught Cheeger's inequality in their classes. I've taught them many times, but several of us have. We might already know that Luca has an amazing set of notes on this topic on his blog. They are probably 10 plus years old, but they are really good. So if you're intrigued by these results and want to learn their proofs, I recommend you check out the blog post. Good. So that's Cheeger's inequality. Luca wanted to make a high-level point here, which I want to discuss next, which is that this robust version of connectivity via lambda 2 was made possible because of this optimization problem that I was referring to at the beginning. In particular, lambda 2 of the normalized Laplacian can be thought of as the solution to the following optimization problem. Minimize the quadratic form of the Laplacian or normalized Laplacian matrix. Quadratic form of a matrix A is simply V transpose AV, where V is an arbitrary vector. Lambda 2 can then be thought of as the minimum of V transpose LV, where L is the normalized Laplacian, where the minimum is taken over all unit vectors that are orthogonal to the top eigenvector, the eigenvector corresponding to lambda 1. For regular graphs, that's just all one. So equivalently for regular graphs, this is saying that lambda 2 equals the maximum of V transpose LV over all unit V such that V is orthogonal to the all ones vector. This is the definition of lambda 2 as an optimization problem. And, in some sense, the connectivity property that we saw at the beginning is analysis of, what happens to the solution when the optimum happens to be 0. But because it's an optimization problem, you might naturally think of what happens when the value is small. And that, in some sense, is what's going on in the analysis of Cheeger's inequality or the proof of Cheeger's inequality. In particular, you can view this optimization problem with only slight massaging as a relaxation of the clustering problem we were interested in the beginning. The clustering problem being separate the graph into two sides so that the fraction of edges that go from one side to another is small. Good. So that was Cheeger's inequality, but let's come back to the observation Luca told us at the beginning in spectral graph theory 101, which was that so one consequence of that is that not just lambda 2, there is a version of the connectivity connection to eigenvalues even for lambda k. In particular, lambda k is 0 if and only if the graph has at least k connected components. Once you look at this result written down on slides, you should ask, is there an approximate version of it, the same story? It turns out there is, and it's called, very suggestively, the higher order Cheeger inequality. Higher order Cheeger inequality says exactly what you might guess based on the previous slide, that lambda k is small if and only if there exists a partition of the vertices of the graph into k disjoint sets such that each set has small conductance, which means that each set is such that most of the edges incident on the vertices in that set stay within the set. Okay. Formally, you can define phi k as the fraction of edges that go into the multi-way cut. And higher order Cheeger inequality simply says that phi k is at least lambda k over 2, the so-called easy direction, and at most square root of lambda k up to this fudge factor of order k square. One interesting regime you should imagine when trying to understand this theorem is k being a large constant. So, imagine you wanted to partition the vertices of a graph into 100 groups so that, the edges that go between the groups is small. Well, higher order Cheeger inequality says that you can do this partition exists when lambda k is small. Not only is this inequality true, but just like Cheeger's inequality, it comes with an algorithm. In fact, the proof itself is algorithmic. The proof itself, in fact, is an analysis of an algorithm, just like Fiedler's algorithm that people were using in practice way before it was actually analyzed. The algorithm is called spectral partitioning, and at a very high level, it embeds the graph into k-dimensional Euclidean space, with respect to the k top eigenvectors. and there's something geometric in this k-dimensional space in order to find this k-way partition. The proof of the higher order Cheeger inequality basically analyzes this algorithm and shows that, it finds a cut of sparsity order k square root lambda k. Given the basic nature of this result, you might guess that this result must have been known forever, but it turns out that this is actually, just about 10 plus years old, and it's one of the landmark results that Luca proved with his co-authors. Now, going back to this point that Luca wanted to make in his talk, which is, whenever you prove interesting basic results in spectral graph theory, there is often a benefit to derive in pure maths themselves by somehow using, the intuitions that we learn when studying graphs and pushing them back to pure mathematics. It turns out that here it actually does work. The higher order Cheeger inequality was actually conjectured by Miklo, who was interested in functional analysis. In fact, he was interested in infinite dimensional analogs of matrices called operators. And this conjecture was key to settling a this conjecture of Miklo was somehow posed in the context of analyzing some Markov operators, some like birth-death processes on trees. So once the higher order Cheeger inequality was proven by Luca and his co-authors, Miklo was able to take this proof and use it as a key component in the resolution of this 40 plus year old conjecture. At this point, Luca wanted to make a conceptual remark, which I will try to relay as best as I can. You could ask, why is this working? We are used, perhaps, since the beginning of our field, in learning deep areas of mathematics and applying them to obtain results in theoretical computer science. But Luca wanted to mention that, this application is not usually vanilla. Usually we have to change the results. And in changing these results, we develop our own intuitions about the objects that we actually cared about. In the context of this result, it's the graphs. And it turns out that these intuitions themselves carry some weight in the sense that they can be powerful in going back and attacking problems in math themselves. One example that Luca wanted to mention here is that, so this is not an isolated incident. There are lots of, by now, there are lots of examples of ideas from theoretical computer science applying and resolving various questions in math. And in particular, Luca wanted to mention the work of Avi Vigdersen at the Institute for Advanced Study in, bringing forth many such connections between mathematics and computer science, somewhat akin to the kind of interaction between theoretical physics and pure mathematics. Good. Any questions before we shift to Luca's second vignette? Okay. So the second thread that Luca wanted to discuss was graph sparsification. So let me, start with the vanilla notion of sparsification called cut sparsification that perhaps many of you might have seen. The idea behind sparsification is to take a dense graph where dense, let's say, means, super linear number of edges in the number of vertices, and approximate some relevant set of properties of the graph by a sparse graph. A sparse graph, for the purpose of this talk, would mean order n edges, or let's say order n polylog n edges. For cut sparsifiers, what this means is that you want to take a dense graph and produce a sparse graph such that if I take any cut in the dense graph, and I go back to the corresponding cut in the sparse graph, then up to rescaling, the cuts are within 1 plus minus epsilon factors of each other. It's important that this notion is relative in the sense that every cut must be preserved up to a multiplicative error of 1 plus minus epsilon. Formally, H, a graph H on the same vertex set as G, is a cut sparsifier for the graph G with error epsilon if for every subset S of vertices, the number of edges that go between S and V minus S in H, the ratio of this quantity to the number of edges that go between S and V minus S in G is between 1 minus epsilon and 1 plus epsilon. Why might you care about this? Well, if you wanted to solve some problem about cuts in a graph, dense graphs might cost you a lot, but if you could efficiently compute a sparse graph sparsifier for it, then you could simply solve the problem on this sparse graph, you would still get a very good solution in the sense that you will be 1 plus minus epsilon accurate, but your computational cost will hopefully reduce. So in general, this is like a very general trick for making dense graph problems be solvable faster. The cut sparsifiers were first studied in the work of Karger, who actually gave a construction with n log n over epsilon square edges to get 1 plus minus epsilon approximation. And the idea of Karger is amazing in the sense that it actually shows that simply independently sampling each edge of the graph G with some appropriate probability actually works. The probabilities are not the same for each edge. In fact, that provably doesn't work. So the sampling scheme they use is called importance sampling, where every edge is given a probability that is somehow proportional to how important it is for the connectivity of the graph. And then once you sample the edges proportional to this probability, you get a n log n over epsilon square sparsifier. In 2004, building on this line of work, Spielman and Teng introduced a stronger notion called spectral sparsifier. Roughly speaking, cut sparsifier corresponds to preserving the quadratic forms of the Laplacian matrix on 0, 1 vectors or plus minus 1 entry vectors. Spectral sparsifier asks you to preserve all quadratic forms, no matter the vector. This abstract notion, which a priori does not have much to do with cuts, was introduced because it was somehow directly useful in solving certain classes of linear systems. That line of work has evolved into its own sub-area now, and there are lots of cool results that Luca will not point out in this talk. In their paper that introduced this notion, there was a complex iterative construction that actually recovered something similar to Karger, perhaps with larger number of log factors. Now, to people who have seen the first two results, the third result will, comes as a surprise whenever you teach it, especially. It turns out that for the spectral sparsifiers, which is a stronger notion than cut sparsifiers, there is in fact a very, very simple proof. If you black box this cool idea called matrix Chernoff bound, if you've seen Chernoff bounds for scalar random variables, it turns out that there is a version of it that holds for matrices. And there is an important sampling scheme that comes essentially from the statement of the matrix Chernoff bound that actually gives you an n log n over epsilon square sparsifier. There's a 2-page proof of this result. So it's an amazing result, at least if you assume matrix Chernoff bound in a black box way. Nevertheless, in these three constructions, the proofs are getting simpler, but this log factor persists. So you could ask, could I also remove this last log factor? And this might appear like one of those log shaving things that we often, frown upon. But this log n, the task of removing the log n from matrix Chernoff turns out to be really fundamental. It's at the heart of several questions in discrepancy theory, lately in coding theory. And, one example is soon going to turn up in Luca's own talk. It's going to relate to this fundamental question in operator theory. For the case of graph sparsification, such a order n over epsilon square sparsifier without the log factor was finally achieved in this landmark work of Batson, Spielman, and Srivastava, again via complex iterative construction. Luca wanted to point out actually a different proof of this result, which in some sense can be, introduces in some sense a very nice new technique in proving such results. This is to Alan Zhu, Liao, and Orecchia. And the idea is to somehow write a optimization problem that constructs a sparsifier. That's not so difficult. I'm not even going to describe what the optimization problem looks like. But the idea, like in some sense, the whole goal is to show that there is a solution to this optimization problem with small number of edges. The idea of this kind of a proof is to invent some appropriate update method, which is actually inspired from works in online optimization. Here it happens to be some version of follow the regularized leader, if you know what that is. But basically, there is an update rule that you analyze and show that it must, because of some potential argument, converge in the requisite number of steps. And there is, in fact, a name for this class of potential arguments. Is called, mirror descent. And there is a general scheme of analyzing such update rules and proving new results with them. The reason Luca wanted to point this out is because this is one amongst several results, especially in discrepancy theory, where you show the existence of an exotic object by analyzing an algorithm to construct it. in some sense, the best and the cleanest method that we know that an object exists is by analyzing an algorithm and show that it actually, converges to this object we're interested in. Good. So for the final bit that Luca wanted to point out here was the connection to a problem in operator theory. Many of you might have heard about it. It's the so-called Garrison-Singer problem. Luca would state for you the version due to Weaver. There are several equivalent formulations. This formulation is the following. Say you are given a bunch of rank 1 symmetric matrices. So basically just vectors, but written as rank 1 forms, V1, V1 transpose, V2, V2 transpose, such that they sum up to identity. And say that each vector is not too large. This bound actually is somewhat intuitive if you think about the equation in the first line as follows. The trace of the right-hand side is n. So if each of the m terms contributed an equal trace, then you would guess that each term would have trace n over m. The trace of a rank 1 matrix is the L2 square norm of the vector. So this condition that each vector is order n over m large in L2 square norm is roughly saying that they all contribute equal trace up to some constant factor slack. The problem asks to find a subset of these vectors such that the subset is close to half identity, and close in the sense of spectral distance. So the spectral norm between the sum of the rank 1 forms in this set S from identity, half of identity, is order of square root n over m. There is maybe a different version which is easier to appreciate. Simply says that you want to split this sum into two parts which have roughly equal sums. If they were exactly equal, the sum of the rank 1 forms on each side would be exactly identity. You want that the two sums be roughly a half of identity up to some small spectral error. Luca won't go into it here, but there are easy arguments to show that this bound on the vectors is required. Because if a single vector is large, you could imagine that placing it on either side will really bias the sum. So the bound on the length of any vector is actually necessary. And actually the square root n over m dependence also turns out to be necessary with not so hard an example. So the key question is, does every collection of vectors admit this? Such a subset S. This originated as a problem about foundations of quantum mechanics. This is like a version due to Weaver, as I was pointing out earlier. And there are several equivalent formulations. The reason Luca chose to present this one is because it's closest to the Batson-Spielmann-Srivastava graph sparsification problem. In particular, the Laplacian matrix of a graph can be written as the sum of edge Laplacians, each of which happen to be rank 1 matrices. So, the question of the Garrison-Singer question is simply equivalent to finding roughly half of the edges that approximate the Laplacian up to a factor half. If you have such a result, you can iterate it and get a sparsifier, each time reducing the size of the graph by a factor 2. So if you apply matrix Chernoff, just like Spielmann-Srivastava, you actually get a version of this result that loses an extra square root log n. The whole business, again, is to remove this root log n factor. And this was done in the work of Marcus, Spielmann, and Srivastava in 2015. Unlike the proofs of higher order Cheeger and graph sparsification, this proof is non-constructive. The reason Luca wanted to point this out is because the final thing he wanted to say is a natural question that comes out of this line of work, which is the last thing I'll point out. Consider graphs where all the effective resistances are the same. Effective resistances is this formal notion of connectivity that Luca was talking about earlier. So imagine that all the edges have the same importance. In this case, you can expect unweighted graphs to be sparsifiers. The sparsifiers of Batson, Spielmann, Srivastava are weighted graphs. But in this case, when all the edges are in some sense equivalent, you can expect unweighted sparsifiers to exist. Nevertheless, the Batson, Spielmann, Srivastava proof does not guarantee them. In fact, the only proof we know that guarantees such unweighted sparsifiers is due to Marcus, Spielmann, Srivastava, in fact, applying this general hammer. Because their proof is non-constructive, we don't know how to construct unweighted sparsifiers, even when they are promised to exist by MSS. And just to stress the point, an example of a graph where all the effective resistances are the same is the plain old hypercube. which is promised to have a linear size sparsifier by MSS, but we do not know how to construct it. There is a paper that Luca somehow did not point out, but I want to point out, is due to Bunsell, Svensson, and Trevisan, that makes progress towards this goal by considering, sorry about that, by considering a certain additive error variant of the requirement. It's a weaker error guarantee. It does not quite resolve the question asked here, but for this notion, they in fact show how to achieve this goal. And their paper is also a good source to read about this question because it poses natural, concrete open questions for achieving the multiplicative error. In fact, even special cases which are interesting. Finally, the last point Luca wanted to make in this regard is that you can think of the plain old expander graphs as unweighted spectral sparsifiers for the complete graph or the clique. So the question that is being asked, the second bullet point here, is, are there analogs of spectral sparsifiers for all graphs for which MSS promises you unweighted sparsifiers? We don't know the answer to this question, and it's a natural open question that Luca asks in this talk. For MSS expanders, meaning for all graphs for which MSS will tell you that unweighted expanders exist, such a result can be achieved. This is there in the paper. But for general graphs, for example, hypercube, this remains open. That's all for the first part of the talk. I'll now hand over to Salil for giving the second part of Luca's talk.
Can you hear me?
Yes.
And can you see the slides? Let me see. Sorry, get into slides working? Okay.
Yes.
Hi, everyone. Now I will present the portion of the talk where Luca recounts his personal journey.
Salil, are you sharing?
I am sharing. On Zoom, I think they can see the slides, so I can.
Yeah, we can see the slides on Zoom.
Maybe. So,
Okay.
Salil, are you
I'll
sharing?
wait a moment.
Salil, are you sharing the screen right now?
Yes.
Oh, we can't hear you. Maybe. Oh, can you increase your volume?
Can you hear me now?
Yes.
All right. And I am sharing.
Ah, perfect.
Okay, yeah, we can start now. Thanks, Salil.
Okay, thanks. Now I will present the portion of the talk where Luca recounts his personal journey, using his own words as he wrote them in his final weeks. I'm presenting from Luca's office here in Bocconi University, joined by Luca's husband, Junsei Jiang, and Luca's Bocconi colleague, Alon Rosen, a dear friend to them who provided tremendous support during these past 6 months. My 3 experiences as an outsider. I have had all the privileges of being born a white cisgender male in a loving middle-class family in a European country. But I have had some experiences being different from the majority, and I will share my personal experience and what helped with inclusivity in my case. I did my undergraduate degree and my PhD at La Sapienza in Rome. This is one of the finest universities in Europe and the alma mater of Silvio Micali. Currently, it is one of the best places in Europe for theoretical computer science. But in the 1990s, there was a pipeline that fed into TCS, at least of the algorithms and complexity sort, that tended to draw students from certain universities in certain countries, like the US, Israel, and India. And I was not part of that. In my 3rd year of undergrad, 1990 to 91, I took a computational complexity class using a textbook in Italian by Beauvais and Crescenzi, which had just been published. The class was taught by Beauvais himself. We studied NP completeness, and the book mentioned that we did not understand the complexity of finding approximations at all. Maybe there's a p-task for the maximum clique problem, or maybe it is very hard to approximate. Later on in the course, the professor comes to class and says, "Remember what I said a few weeks ago about approximability? I heard that a paper came out that shows that indeed the maximum clique problem does not have a p-task." He was referring to the famous Fege, Goldwasser, Lovas, Safra, Segedi paper that established the connection between PCPs and inapproximability. FGLSS indeed was published in Fox 1991 and was circulating in the spring of 1991 when I was taking the class. I had studied mathematics, where the most recent topic we were learning was Lebesgue measure, and the other topics were 1 or 2 centuries old. The idea that you could have a mathematical field where the results of a just published textbook are overcome in months was amazing to me. I wanted to do an undergraduate thesis on hardness of approximation, but the work was impenetrable. I still did a thesis in computational complexity with a young new professor, Pier Luigi Crescenzi, and I decided to continue with a PhD. There was continued progress in the mid-90s on PCP and hardness of approximation. At some point, Balari, Goldreich, and Sudan had a series of improved results, and Oded Goldreich was unhappy that they relied on lore that had never been properly written. They wrote their paper with all the details, all 100+ pages of them, and released it online. It became my Bible. Thanks to the BGS paper, I could understand what was going on, and I had some ideas. I cold emailed Madhu Sudan, who took an incredible chance on taking me on as an intern at IBM Research in 1996. The ideas worked out, and later he helped me get a postdoc at MIT. At MIT, I continued to work on PCP, but an amazing new result of Russell and Payazzo and Avi Vigderson on de-randomization had come out, which relied on a series of older papers. We set up a reading group with the goal of understanding and writing down everything, and it was incredibly productive. I ended up proving my biggest result, which helped me get the job in Berkeley. Even in Berkeley, they certainly took a chance in hiring someone with only 2 or 3 significant results, a person they couldn't know so much about and whose future trajectory was unpredictable. The points I want to make are the following. Clearly, one is to give someone with an unusual background a chance, like Madhu and Berkeley did with me. But also, a less obvious point is the importance of full exposition. If an area develops some lore that only insiders know, then it makes it prohibitively difficult for others to join. BGS made me develop a lifelong passion for exposition. Just before I moved to Berkeley, I came out. At Berkeley, I was rather visibly out on campus. There was an out list of LGBT faculty and staff posted online that I joined. There were several LGBT groups that organized events, and I always tried to attend them, sometimes bringing straight allies. Without going knocking door to door telling people I was gay, I was always open about that. And I tried to make it well known that there was at least one gay professor in the ECS. I did not want to make a big deal out of it. It was 2000 and everybody was super supportive, but it was unusual. I had few other examples of what an out theory faculty member is like. In those years, there was a sudden surge of gay grad students at Berkeley. Or perhaps there wasn't, but there was certainly a sudden surge of grad students who told me they were gay. Here, the point I want to make is that visibility itself makes a difference. Of course, this experience is hard to generalize because a lot of minorities are already visible minorities without an option of being in the closet. In 2012, it was the 100th birthday of Turing, who was out in a way that was totally ahead of his time. This was a strong part of his identity and a huge part of his story as a person, whose thinking was consistently in the future. Lots of scientific events were organized in 2012 to celebrate Turing's legacy, with hardly any mention of it. I resolved to put the gay back in the Turing Centennial by hosting on my blog a series of 8 guest blog posts where LGBT colleagues from TCS and math wrote about their experiences in the field. This simple initiative had a huge impact. Years later, I kept randomly meeting people who had seen it and for whom it had been meaningful. This again brings out the point I made about visibility making a difference. In addition, small initiatives also matter and can have a surprisingly large impact. As you can see from this talk being given by others, I have had some recent experience with illness and disability. This is my first experience being in a visible minority. Though some issues with visibility are still present, and I felt it was important for myself to overcome them right away. In some sense, I came out again, this time as a sick person. Indeed, I do feel that our society does not like to think about illness, and that there is a strong pressure to present a healthy and capable identity. This is not totally different from how little we talked about sexuality and from the pressure to present as having a normal sexuality 20 years ago. This is also the first time that I've experienced being in a minority whose accommodation may require structural changes, not simply visibility and nudges. My brief experience is that rather than having big but inflexible policies, it is best for institutions to be flexible, to do concrete things, and to be willing to spend money. I have noticed a similarity to the feedback I've heard from mothers and parents about the support that they would find most useful. Individualized solutions like free teaching discounts, teaching buyouts, pay for daycare at conferences, to be allowed to pay for business class from grants to do shorter trips and to be less time away from home. Bocconi was willing to find individualized solutions for me and to invest in them. I wish I could end the talk with advice on how to make this happen more broadly, but I'm afraid this is above my pay grade. I will leave this as the open problem of the talk. Returning to myself now as Salil, it is tempting to go on and on about all that Luca has given us, both personally and professionally, and how dearly we will miss him. But this talk was one of Luca's last gifts to us, and it should be kept the way that Luca wrote it. So I will limit myself to saying, on behalf of the theoretical computer science community, thank you, Luca, for inspiring us for so many years, and for the inspiration you will continue to give us far into the future.